welcome you to the first edition of the Joys of Anatomy. If this is your first time with us, I'd like to invite you to grab a brush and some paint and with us while we talk about the neurophysiology, especially the impulse conduction. And if you've been with us before, I'd like to thank you for inviting us to paint another series with you. So I'll tell you what, let's get started. To start out, let's have them run the colors across the screen that you need to paint with us at home. They're right here. As they're doing that, let me show you what I have set up here today. I have a standard canvas that I covered with a thin layer of liquid clear. Let's have fun today. So with the old 2-inch brush, I'm going to be putting very, very little paint and just grab a tiny bit of that potassium purple. Now, very gently, I'm going to begin by applying the same color to this upper left corner. This is going to be the base for our neuron. In order to explain the steps involved in a neuronal impulse conduction, I think we need to start by familiarizing ourselves with the structure of a neuron. I am starting by making dabbing motions in order to create some sort of a circular cell body. This is known as the soma, or cell body of the nerve. Now let's dip into some of this dendrite black and with little flicking motions, start the formation of neuron dendrites. The dendrites are an essential part of the neuron because they receive nerve impulses. Now it doesn't matter how perfect your dendrites look at mine. They're just little, and it's okay if they look a bit different because in our world, we don't have mistakes. We just have happy accidents. Now, when you're happy with your dendrites, let's take a clean brush and dip into some of the axon orange. In a smooth, relaxed motion, I'm going to lay down the paint all along the center of the canvas horizontally to create the axon. It's okay if you got some of that dendrite inside of there. It's fine. The axon conducts electrical impulses known as action potentials away from the nerve cell body. Action potentials are caused from when different ions cross the neuron membrane. Next, we will finish the neuron by adding the axon terminals, which send nerve impulses. Axon terminal. I love the way that sounds. Terminal. Going back to our friend, the 2-inch brush. In addition to the axon, let's also paint a visual of resting membrane potential. We'll start by creating the phospholipid bilayer, or cell membrane, which is composed of phospholipids and voltage-gated channels, as well as sodium-potassium pumps. Now I know these don't look quite right yet, but wait till we just add some detail with the action potential white. Okay, now we're going to add some vertical lines inside the black we just laid down to create the phospholipids. Time to add our sodium-potassium pumps. The sodium-potassium pumps are responsible for setting the concentration gradient. And when a neuron is at rest, sodium-potassium ions are constantly being pumped in and out. With a clean 1-inch brush, let's pick up some of this sodium silver and make 2 big N-like shapes in between the gaps of the phospholipids.
Above the membrane is outside the cell. This is where there is higher concentration of sodium ions. The inside of the cell is where there is a higher concentration of potassium ions. To remember this, let's paint sodium ions above the membrane and potassium ions below it. With a small pointed brush, we can go ahead and dip it into the sodium silver. This is when you can really let your brush kind of run free. Just place the sodium ions in the shape of circles along the area above the membrane. Make sure there are quite few there and only some below the membrane. Now let's get a clean brush and pick up some of that potassium purple. Do the same thing that we just did for the sodium ions, but make the potassium ions little triangles. The reason that there are some ions of each type on both sides of the membrane is that they do not like to be surrounded by other ions of the same kind. Ions move along a chemical gradient when going from an area of higher to lower concentration. Ions move along electrical gradients when they move toward an area of opposite electrical charge. Both chemical and electrical gradients make up the electrical chemical gradient. Now, to finish up our membrane, we need to add some voltage-gated channels. Voltage-gated channels open and close in response to changes in membrane potential. Alrighty, now that we have our neuron and cell membrane model painted, let's talk about action potential. If you're still painting along with us at home, I want you to grab a clean liner brush so we can make a little graph of action potential. Start flat for a while because we are at resting potential, then make a steep upward stroke. This is depolarization, which is when the sodium channel opens and there's an influx of sodium. Next, create a little curve at the top where we left off and bring it down past the flat resting potential line we made earlier and up into a wide U shape like so. This steep downward stroke we made represents repolarization, which is when the sodium channels close and the potassium channels open. When this happens, there is a pretty big, large influx of potassium ions, efflux. The big U shape we just painted right after repolarization is hyperpolarization. During hyperpolarization, membrane potential dips down to around negative 80 millivolts, which is lower than resting potential. Make sure you note that there are two refractory periods. The first is the absolute refractory period, which is when a neuron generates a new action potential. The second is a relative refractory period, which only the exceptionally strong stimulus can cause a new action potential. Repolarization occurs after this refractory period. The final process we will be painting today is synaptic transmission. Why don't we grab a new brush for this one? As we know, the operation is not connected by synapses. So when a nerve reaches the axon terminal, it sets into motion a chain of events that trigger neurotransmitter release. To make this a little clearer, let's go ahead and paint this process. First, let's grab a clean 2-inch brush and dab on some of that refractory period red. In the upper left-hand corner, let's start painting our presynaptic neuron. This neuron fires a transmitter as a result of action potential entering in its axon terminal. Alright, now inside the presynaptic neuron are the synaptic vesicles, which contain neurotransmitters and release its contents into the synaptic cleft after fusing with the membrane. To paint these, let's grab another clean liner brush and dip into some of that axon orange. Inside the bell shape we made, go ahead and drop in some of that spheres to create our synaptic vesicles. Next, dip inside some of that potassium purple, and on the edge of the postsynaptic neuron, kind of off to the side, paint a small squarish blob. This is a calcium channel, which allows a surge of calcium to flow into the axon terminal. This triggers a release of neurotransmitter, which opens ion channels on the postsynaptic neuron by binding it to a receptor. To complete the picture, let's grab a clean brush and dip inside some of that dendrite black. All the way bottom right corner, let's create the shape that complements the bell shape of the presynaptic neuron and fill it in. Now that we have our postsynaptic neuron, which receives a neurotransmitter after it was passed after the synapse, the last thing we need to do and paint are the ion channels. With the liner and some action potential white, paint little beetle-shaped dots along the edge of the postsynaptic neuron below the presynaptic neuron.
Hope you enjoyed this one. It's a very simple little painting. If you've never painted before, this one you can do. From all of us here, I'd like to wish you a very happy ending. God bless you, my friend.